to do to start off today is I'm just a little bit concerned that we're not all exactly on the same page with what's happening and how we're building the geology of South Africa. And a lot of this goes back to understanding the geological timescale. So I just wanted to kind of, before we get stuck into the lecture today, because we're moving on quite rapidly today, kind of through geological time and leaving this Archean Proterozoic world behind and moving through into the Phanerozoic and the Cambrian. So just as a kind of a recap, I want to recap this and kind of summarize what we've done so far. And I think it's a good time, here we go, it's a good stage now today to do this. Before we do that, I just want to have a little bit of a recap of geological time, just to make sure we're all on the same page. Alright, so imagine we're looking at the geological time scale, and these are the longest divisions of geological time. So what are there's four, and these are the longest divisions of geological time. Can anyone tell me what we call those? Not eons, yeah, spot on. So these are the eons, and there's four, and they're the longest ones, the longest periods of geological time. So we're just going to focus on these, the bottom ones to start off with. So the oldest one is the Hadean. And this is from kind of the start, when we've got a solid Earth, from around 4.6 to around 4 billion years ago. So this is a very long time period, and we don't have a good rock record from this, and we can kind of move on from there. But then in the geology of South Africa, this next time period, the Archean, is important. We know that's from 4 billion to around 2.5 billion years ago. And then what comes after the Archean? I thought I heard someone muttering it. What's next? Proterozoic, exactly. So protro means first. And zoic is to do with life. So this is the Proterozoic, and that's from 2.5 billion. And there's this big boundary here, this big junction, which is at around 543 million years ago. Okay, so these time periods collectively are known as the Precambrian. So, yeah, all of this collectively, I need to write here, but all of this time, so from 540 million years ago, all of this collective time is also called the Precambrian. And the reason it's called the Precambrian is because if we go up here, recent eon, so this is from around 543 million years all the way up until, so this is where we're sitting today, and this is the Phanerozoic, which is the most recent. Eon is divided into 3 eras. Okay, any takers for what these are called? in turn divided up into periods. So those are the small, that's like the next. And the first period of the Paleozoic is called the Cambrian. This is named after a part of Wales, Cumbria in Wales, which is where the rocks are found there. So, because this is called the Cambrian, and this is where we see the first appearance in the geological record of kind of life as we know it, multicellular organisms. And it's called the Cambrian explosion, and it's a big deal in paleontology. So, because this period is the Cambrian, everything before that is called the Precambrian. So it's useful if you're working in much younger time periods, because you can be just like all of that geological time is the Precambrian. Not so useful in South Africa, because most of our geological record is in here. So if we classified rocks in South Africa as Cambrian and Precambrian, we'd have, you know, a little bit of Cambrian and younger, and so it's not really good for us in South Africa. But it's just to put it into context for you when you hear about people talking about the Precambrian. That's what the Precambrian is. And then, just while we're dividing the Phanerozoic up into periods, then the Cenozoic is the important two periods in the Cenozoic is divided into two. And the older one is called the Tertiary. And then the youngest one is called the Quaternary. And then an even younger, the last, the smallest part of geological time is an epoch. And the Quaternary is divided into two. And the older one is called the Pleistocene. And then the most recent one is called the Holocene. You would need to know these ones. So you don't, the geological time scale that I gave you, you don't have to know every single bit of detail on that. But what's on the board, this kind of summary, I would expect you to be vaguely familiar with. Just for the Phanerozoic, that it's important to know the eras. I'm not going to ask you minute detail of what's happening in the Archean and stuff. But this overview that I'm giving you now, this is what I would expect you to have an appreciation of, at least. And if we put some time onto this, so this here, this boundary here between this Mesozoic and the Cenozoic, this is a big one and is important. This is at 65 million years. And this boundary is important because this is the extinction of the dinosaurs. So the life on Earth changes enormously. So this is up until basically here, the Mesozoic onwards, this is the kind of the time of the dinosaurs. And then there's this huge extinction event at 65 million years ago, and that's when we get the rise of mammals after that. So this is a big turning point, and this is a big one. So a little hint, like a good exam question would be, what happened at 65 million years? And then this boundary here, this is 1.8 million years ago, and that's the beginning of the Quaternary. And then the Holocene starts at 15,000 years ago. So this is into much more recent time. And then...
What is the Holocene?
The Holocene is the most recent geological time period. And most geologists would say that we are in the Holocene at the moment. However, climate scientists are adding a new epoch here, which is right basically where this line is, and they're calling that the Anthropocene.
It means?
So the Anthropocene, which they argue starts in about the 1950s, and this is from when humans have started to have an impact on the climate. So if you look at global warming and carbon emissions, the big increase in carbon emissions with the Industrial Revolution really begins to happen from the 1950s. And this is where humans began to actually impact on the climate. So it's not an officially recognized ecological time yet, but it will be. And this is really what we're living in now, is the Anthropocene, where we have a human-caused climate. So not next week, but the week after, we're going to look at some climate change stuff, because it's very interesting to understand modern climate change and future climate change. You need to have an appreciation of geological time and how the climate has changed in the past. So that's why I was a bit hesitant to say the Holocene is the most recent geological time period, but this has just been the last couple of years. Yes.
Asking about the 65 million year mark.
Yeah.
Dinosaur extinction at the end of the Jurassic period, because there was a period between the Jurassic and the Tertiary.
When we finally discover Mars, that a new, when we finally colonize Mars, the new era.
Maybe a Martian epoch when we actually leave planet Earth. But that wouldn't be Earth time then, would it? Like. Okay, so this is geological time in a nutshell, and I hope this helps make sense of it. And if you have any questions, now is the time to ask. But then what I wanted to do next was just to put in context the South African geology that we've done so far. Because, yes.
I heard that there's currently a mass extinction event happening in the Anthropocene.
So Richard Leakey is a famous conservationist and paleoanthropologist who studies human evolution. He's been arguing that we are in the middle of the sixth extinction, and it's you can trace its beginnings even back to the 1950s. That humans are changing the planet so much, and so many animals are going extinct, that if you look at it relative to previous extinctions, that we would be in the middle of a mass extinction.
So which animals? That's what I mean.
Lots of animals. Ones in the sea, the rainforest animals. It's the habitat destruction, basically. There's so few pockets of Earth which you have just like natural environments there. Anyway, before we get all depressed about conservation, let's go back to Archean geology. Okay, so the Hadean, we don't see much of the Hadean. There isn't a big rock record from the Hadean, so we're not going to worry about it too much. And today we're going to look at this Cambrian explosion, and we're going to look at this late Proterozoic period. That's what we're going to do today. But before we get there, I just wanted to put in context kind of what's happening in South African geology.
That's what I was going to ask.
Okay. You're a step ahead of me. All right. So the very first thing we did in South Africa, the first things we looked at was like 3.6 3 billion years ago, and that was Barberton. So in Barberton we looked at the greenstone belt. So the greenstones are volcanic and sedimentary rocks that had formed in a shallow basin, and we've got a hotter mantle and these special rocks coming up to the surface. And then these get deformed, and we've got this early plate tectonics, which is happening fast because the mantle is that much faster. And by the end of this time in Barberton, we have all these massive granites, this huge emplacement of granites, which stick together as a number of other small greenstone belts. And so by about 3 billion years ago, we have the Karp-Val craton. So it's named after the provinces, the old South African provinces which were over it, the Cape and the Transvaal, so Karp-Val craton. And basically this is just like a proto-continent, so it's this big lump of granite with bits of greenstone belt in it, and it's sitting in a sea basically of oceanic, basaltic oceanic crust. And it's a very early proto-continent. And then what happens afterwards is that we have a number of things happening on top of this ancient craton. Yes?
Why was it different? Like, why was it not the same as the oceanic basaltic continental material?
So it's, the continental crust is granite. So it's a different type of magma, basically. So it's different minerals that form the granite, and they're less dense and more buoyant and have more silica. And so it's basically, by about 3 billion years ago, we've got the beginnings of the continents forming. So by 3 billion years ago, we've got our Kappa craton, and then we have various forces happening, mainly divergent forces, which are causing, from the convecting mantle underneath, which you get this early plate tectonics, and we get rifting on our Kappa craton and a number of sedimentary basins forming on top of it. And so the oldest of these basins is from 3 billion to around 2.7 billion. And this is the Wits basin, so the Witwatersrand basin. And this is the Witwatersrand supergroup. So those are our gold-bearing rocks. Yeah, everyone remembers the Wits. And then we get, as the Witwatersrand basin basically kind of fills up, we have the collision with the Zimbabwean craton. So that's where you've got another craton kind of sitting over here. And it's also on.
So this is
More ocean crust. And basically this Zimbabwean craton is moving faster, and the two cratons collide. And it's all to do with the plate tectonics, with the plates moving around and moving the cratons. Like the video I showed you with the luggage on a conveyor belt. Alright, so then we get rifting on the Kappa craton, and by 2.714 billion years ago we have the Ventersdorp lavas. And this is a huge outpouring of these lavas at surface, and they basically cap off the Witwatersrand supergroup. And this has definitely helped preserve the Witwatersrand supergroup. That's why we have such, these rocks are super old. They're 3 billion years old, and they're still preserved, and it's partly because they were capped off by the lavas from the Ventersdorp. So then what happens, we have the Ventersdorp lava comes up, and we've got on our Kappa craton, you can imagine this is the craton, this is the granitic basement, and it's been filled up. This is the Witwatersrand, and we've got the conglomerates with the gold-bearing rocks in them. And then we have rifting in the craton, and you get lavas coming up to surface, and basically the Ventersdorp lavas cap off the Witwatersrand supergroup. And then these geological processes continue, and we get renewed rifting, and a new basin forms, and we get a flooding of a shallow sea, and we have a new basin forming. And underneath this basin, you have the Ventersdorp, and the Wits and the granite is all sitting underneath. So we're building up this sequence of rocks. And then these rocks are towards the end of the Archean, so 2.6 to 2.0. So this is spanning this time into the early Proterozoic, and this is the Transvaal supergroup. These supergroups of rocks got their names from the old South African provinces, because most of this outcrops where the Transvaal used to be. So this is, in the Transvaal supergroup, we have the Dolomites, because it's a shallow marine setting. You have the limestones, which get turned into dolomites, and these dolomites erode, and we get sinkholes in them today. So for you guys as engineering geologists, there will be engineering problems on dolomite, or civil engineers, and there'll be, so problems with roads, sinkholes, and and the Dolomites, yeah, where the old Transvaal province used to be, and all of these blue rocks, these light blue rocks on the map, these are all the Dolomites. And they weather to get that like elephant skin weathering, so that's how you would spot them. Okay, so that kind of caps off, that's the Archean geology of South Africa. So we have this ancient basement and then two big basins, the Witwatersrand supergroup and the Transvaal supergroup. And then we have two other things which happened during the Proterozoic, which we talked about yesterday. So at around 2.059 billion years ago, we have the Bushveld intrude. Bushveld igneous complex.
Question. Just out of curiosity, there's volcanoes erupting right now, right, in Hawaii.
Yes.
So doesn't that also have some part of formation, or is it?
Yeah, so the Hawaiian volcanics, the rocks that are literally forming today in Hawaii, they would be, we call them Holocene age. And those, yeah, I mean, you get rocks forming yesterday, I think they're brand new. Alright, so we have the Bushveld igneous complex, so my drawing's getting very messy here, basically, but we've got another basin here, and this has got the dolomite in it. And then into all of this, above all of this, we get this big Bushveld intrusion, and this is the Bushveld igneous complex. And that's got the platinum group element. And then, unrelated, but shortly afterwards, is the Vredefort impact structure. So this is everything that we've done so far, kind of how it all fits together. And this brings us up to where we are for today's lecture. So we've really focused, we've just been staying in the Archean, we've moved into the Proterozoic, and what we're going to look at now, so we've got our Karfval craton, we've got these various basins and this huge igneous intrusion. Yes?
Why do we say the Proterozoic started at 2.5 when we have at 2.0? If you said it started at 2.5, right? So why do we have 2.02 or something?
So this is when the Proterozoic starts in geological time, and in yellow this is the age of the Transvaal basin. So the Transvaal basin started at the end of the Archean and then went through into the Proterozoic.
Yeah.
Does that answer your question? Any other questions? Yeah.
Just next to C, and there's, I can't really see it with the Q, but immediately next to that,
Quaternary.
immediately next to quaternary, I can't actually read.
No, sorry, my writing's too small. It's Pleistocene and Holocene. I'll write them again. So in the quaternary,
Quaternary.
Quaternary is divided up into two epochs.
And this is
The Pleistocene and the Holocene. Okay, so now we're going to look at the rock record in South Africa and what's happening at the very end of, we're going to pick up and look at the end of the Proterozoic and this early Cambrian period. So this is this summary map which we're still growing, still working on. And so this is, we've got the Karfval craton with these various things that have happened on top of it. The Zimbabwean craton collided with the Limpopo belt in between. And then what happens is that to the northwest, the Congo craton so that's why the Congo Basin today has gold and diamond reserves, and it was a similar setup to the Karpal Craton. But this Congo Craton is moving quite fast, and this begins to collide with the Karpal and Zimbabwean Cratons. And during this collision, we have rocks that form in basically a shallow sea between these two cratons, and then when the cratons actually collide, we have this huge belt of deformed rock marking the collision and the suture between the two cratons. And this is called the Euclidean belt. And if we go back to look at the geological map of South Africa, this is what we see here. So these rocks here inside the circle, these are all part of the Ubendian belt where it surfaced, and this is from the metamorphosed and deformed rocks from the collision of the Congo Craton with the Karpal Craton. And this is what they look like in this Namaqualand area. So these are around 1 billion years old, so just as fitting in here in this end phase of the Proterozoic. And they are high-grade metamorphic rocks, so they've been heated up to temperatures of over 700 degrees. Yeah. Oh, that's a tough one. There's no simple answer. There's no sort of threshold that's controlling it. It's just, I guess, what's been happening in that part of the world geologically and how much granite there was to stick together the greenstone belt. And those diagrams I've been showing are kind of cartoon reconstructions, but it is based, there is a huge craton in the Congo today. Okay, so this is in the Namaqualand, and this is what the rocks, this Ubendian belt, and they're about a billion years old, and this is just the high-grade metamorphic rocks and what they look like in the field. And this is another field photograph. And we have the Namakwa Natal belt, which is also what these rocks are called, because we get them outcropping, some of them in KwaZulu-Natal today and in this Namaqualand region. And they're these deformed rocks underneath. And you can see on top they're overlain by horizontally bedded sediments. And these are called the Nama group. And the Nama group, these deposits form at the very end of the Proterozoic and the early Cambrian. And where we've had this collision between the two cratons and these highly deformed rocks, then on top of that we get these shallow basins where we have the Nama group rocks forming. The other group that we have in the setting, these two shallow basins, we have the Atabi group, and they've also been folded. So there's a lot of deformation on this kind of edge of the craton environment. And this is just a field photo showing incredible folded sediments of the Atabi group. Incredible outcrop because there's not much vegetation. Alright, so then what's happened then basically, and this is where we're looking at Namibian geology. So this is a map of Namibia, and to the south here we have that Ubendian belt, the billion-year-old deformed gneiss. And then we get these two basins which formed in Namibia. So the older one, so you can see, is around 750 to 550 million years old. So this is just as we're going, this is basically sitting just at the very end of the Proterozoic. And it's a shallow marine environment, so we get limestone and dolomite forming. We also have glacial tillites, and this is where you have, these are the rocks that are formed by glaciers flowing into the shallow sea. And then following in geological time, we have another younger basin, which outcrops in the northern part of Namibia, where we have sandstone and limestone. Is that this is zooming into the geological timescale. So we're looking at the end phase of the Proterozoic and the early Cambrian, which, as I said, is this first period of the Phanerozoic. And so the Atabi group are these older rocks from around, or on this It's 750 to around 500. And then the Nama group is on top of that. And what happens is that quite amazing animals begin to evolve, and this is a major change in the evolution of life. And in this very end phases of the Proterozoic, we have what's called the Ediacaran fauna, and it's also called the Nama fauna. And these animals we're going to look at, I've got a little video which explains them. And this is some of, because prior to this, all we've had are those cyanobacteria forming the stromatolites, and there's been no other record of life. And then in this little time period, which is preserved in the Otavi group in Namibia, we have the first evidence of kind of multicellular life. These are very strange looking creatures, and we'll see them more in the video. And then we have this major switch here, where we go from the Precambrian into the Cambrian, and we begin by the early Cambrian to see the Cambrian fauna. And these are multicellular animals, and they're kind of the ancestors of all life on Earth. And it's when, although they were very strange creatures which went extinct, it's kind of the building blocks of life as we know it today. And so this is a huge switch in geological time, where we switch over to having multicellular complex organisms. And what happened, the change of why we get suddenly this Cambrian explosion of life, is a major question for geologists. So these are some photos of showing this is what the Ediacaran fauna look like. So this is a fossil. This is a centimeter scale, so this thing is about that big, about 10 centimeters. And it's these, they look a bit like sort of ferns, although they're not. These kind of multi-frond, strange looking creatures. And then this is a photomicrograph on a much smaller 500 micron scale of a very early sponge, which would be a multicellular organism, and it's from a more complicated animal. So, let's see.
A mere 542 million years ago, the Earth's landscape was a barren wilderness. 4 billion years after the planet's creation, no animals lived on the land. The most developed organisms were simple animals living in the oceans. Something extraordinary was happening in the seas. Over a period of 20 million years, at the beginning of a period called the Cambrian, an explosion of new animals developed below the water's surface. These later gave rise to most of the diversity of animal life that now exists on Earth. But the cause of this sudden burst of life, which geologists call the Cambrian explosion, remains a mystery.
The Cambrian explosion was really biology's big bang. Things went from moving very slowly along the seafloor without any predation to suddenly all the different type of ecologies that we find today.
Remains a mystery.
The Cambrian explosion was really biology's big bang. Things went from moving very slowly along the seafloor without any predation to suddenly all the different type of ecologies that we find today. Life literally exploded.
We don't really know. There are many different possibilities, different hypotheses, and we've got to remember that cause and effect are often difficult to disentangle.
So what happened exactly? To try to understand it, you need to look a little bit farther back in the history of the Earth, to the Ediacaran period, which preceded the Cambrian. It was during this time that the first large animals evolved, but they were shellless.
Before we go into what's called the Ediacaran times, and this is an extraordinary where we have the seafloor populated by basically weird creatures, and quite frankly, we're not quite sure whether they're animals or something else entirely. These are organisms which seem to have mostly survived on absorbing nutrients from the seawater itself. They may not have had any gut, may be able to move. These creatures are principally soft-bodied, that is, they have no skeleton. And then they seem to more or less disappear as the Cambrian explosion kicks off.
After 45 million years of slow evolution, those weird creatures suddenly disappeared, to be replaced by those of the Cambrian. The first echinoderms appeared 540 million years ago. Brachiopods followed after some 10 million years. The most iconic fossil joined the explosion towards its end. It showed up a few million years later. There are a number of theories about what happened that enabled these creatures to appear.
Suggesting that one of the factors that holding back the evolution of animal is the availability of oxygen. Photosynthesizers, things like cyanobacteria, algae, plants, make oxygen and organic carbon, and once the organic carbon is buried in the sediment, the oxygen is released in the ocean and the atmosphere for animals to use.
Prior to the Cambrian explosion, oxygen levels may have been too low for large active animals to survive. Once those levels increased, larger animals were able to survive and proliferate.
Then animals burst and diversified in many different forms.
Evidence to support this theory of higher oxygen levels is scarce, but there.
So they go on into some more complicated things. But I just wanted, it kind of puts it together nicely, looking at this big shift from this Precambrian world into the Cambrian and the Cambrian explosion of life. So what we're gonna do from now is look at the Phanerozoic geology of South Africa. So we're going to leave this Archean Proterozoic world behind and look at the Phanerozoic of South Africa. And some of the most iconic rocks of the Phanerozoic are the Table Mountain group, famously exposed in Cape Town. So I'm not going to start this today. We'll pick this up next week. So any questions?
Yeah, I had a question about the outcropping of the cratons.
Yeah.
Because of the layering, it feels like there was a lot of layers, so why do we see this stuff very, very
Like the Witwatersrand and the Transvaal groups were never buried very deep. They've been buried a little bit and then eroded to the surface, but they were never buried very deep in the first place.